Today we have Julian McAuley, who's one of our own. He's an assistant professor in the computer science department. And Julian's research really looks at how to model and predict human behavior by analyzing large volumes of online activity. And he's going to talk about a number of projects in that space. When I first found out about Julian, people told me you can go to his website and there's a live camera feed of him at his desk.
Not right now.
And so I went up to your website, and I went up like a half a dozen times, and he was never at his desk. He wasn't there. So that was kind of funny. Although I went up there yesterday, and then you were working away.
Working very hard, I trust.
Trying to earn your tenure.
Yeah.
Okay, welcome.
All right, thanks a lot. Yes, as Stephen says, my research is all about trying to build these models of human behavior, and specifically models about how humans interact with things or with each other. And the most common application of this kind of research is things like recommender systems. So you can build models that estimate how people interact with products or content. And if you can build such models, you can effectively recommend things to people. So we've all seen recommender systems somewhere or other on the web, even if we didn't know they were called that. These are the kind of systems that do things like the following. Say this is from one of Amazon's recommender systems that tells you which movies you might like to watch on the basis of what you've watched in the past. So I don't know, can you guess what I watched in order to get these recommendations? I think it was Iron Man 1 maybe? No, Iron Man 1's in the suggestions. I think it was G.I. Joe 2 Rise of Cobra. And it was garbage, but I did watch it to the end, so maybe these recommendations are somehow justifiable on the basis that I did that. So that's kind of helping me to discover new content. This is another set of recommendations, also from Amazon. You watch Harry Potter 1, it recommends Harry Potter 2, Harry Potter 3, Harry Potter 4, Harry Potter 5, Harry Potter 6, Harry Potter 7, Harry Potter 7 Part 2, right? So it's a different type of recommendation. It's probably not helping me to discover things I didn't know about, but in this case, it's more like a piece of the user interface that's just surfacing things that I'm actually likely to click on next to a prominent position. Yeah. This is another type of recommender system. Again, still from Amazon. This is saying, because you're looking at this item, you might want to purchase this item that would somehow form an outfit. And this is on the basis of things that have frequently been co-purchased. So a little bit different from before. I'm no longer trying to say, what's a good personalized recommendation for me, but rather I'm trying to discover this global property of what items go together. And that makes a different kind of recommendation. Also, there's things like using recommender systems to build personalized experiences, playlists of items that go together. Also, the thing on the right of this figure, the advertisement, that's maybe the result of a recommender system too. There goes everything.
Just feedback.
While I wait for the slides to come up, broadly we have these recommender systems that the goal is to help us find things that we like as opposed to things we don't like, so that it can somehow surface things to the most prominent position possible. So this can be used for a variety of reasons: discovering new content, surfacing old content or content that we already know about to a prominent position for the sake of building a better user interface, finding what goes together, developing personalized user experiences, and more generally just saying what are the things we like versus the things that we don't like. How are you going to do that? You're going to need to build some model, which is where machine learning comes in, that says how can we explain people's preferences, their opinions, and their behavior, and especially how can we explain relationships between users and things, and maybe things and other things, and how can we build models of those interactions. Okay, so I think the next slide requires actually being seen by people, so we can wait for the room to cool down enough. This is what a recommender system looks like. You sort of think about this black box, which is really our machine learning problem. This is our model of people, preferences, and interactions. And then the recommender system, that's kind of just an application. It's not really the scientific problem, right? It's something we build on top of this black box. And of course, what's scientifically interesting is to say, how can we actually understand the dynamics of people's preferences and their interactions with things? And if we can do that, then there's all kinds of different applications we can build. So Today I'm going to talk about a very specific type of recommender system where we're going to be using the visual content of objects to make recommendations. So that's going to be useful to do things like recommending clothing, which is mostly what I'm going to talk about. So I'll talk about some of the very basic background models in recommender systems. Then I'll talk about how can we make these things sort of aware of visual features and also aware of how people's preferences or fashions change over time. And then I'll sort of switch to this other type of recommender system where instead of recommending items to users, we're recommending items to items in order to generate outfit recommendations and things like that. Okay, so this is part of a very broad line of research that we do in my lab where we try to build these models of users, items, interactions, and especially models of very high-dimensional, difficult to understand content, right? So that could be text, it could be music for that matter, it could be people's social networks, it could be time series. This is just one case where we're going to look at visual features in particular. I figured that would be the most interesting for a design talk, right? That being said, we're mostly going to build these on top of these kind of black box, very high dimensional visual models. This is one called a convolutional neural network, which sort of spits out these incredibly high dimensional image features that somehow describe all kinds of characteristics of the image in question. So its color, its shape, its, I don't know, is it bright, is it dark, is it a shoe for that matter, all kinds of things. We're going to try and build recommender systems that can use this very high dimensional content to make more effective recommendations. And in terms of data, this will be using this big Amazon data set we collected last year. It's a pretty comprehensive collection of US products. So we have about 9 million products, all with product images, which is kind of relevant for this talk, by about 20 million users. And what's maybe more relevant is you have 140 million reviews, which are kind of describing the relationship between a user and an item. Did they like something or not? And 300 million of these sort of co-purchase recommendations, so what things go together. And you can download all that data set from my webpage if you're keen. Fortunately, after we did this, Amazon made the website almost impossible to crawl, so I have a nice monopoly on this data. Okay, so just starting with some of the basics, how does sort of the traditional style of recommender system work? If we're trying to estimate users' preferences towards items, I mean, this is what our actual problem setup looks like. We're given some user and some item, and we'd like to estimate something like, I don't know, a star rating. That's a pretty explicit signal of a person's preference. What we're actually going to end up doing today is maybe even a slightly simpler task, which is to say, given a user and an item, would they purchase a product? So we want to spit out true or false if the user would positively interact with that item. And we'll actually do some smooth version of this where we predict a value between 0 and 1. So we get something like, what is the probability that a user would interact positively with an item? If we can estimate that function, we can build a recommender by saying, let's surface the things they'd be most likely to interact with. And the way that all recommender systems work is to try and somehow uncover latent relationships between users and items. So if you can think about building a recommender system for movies or something like that, what would you want to do? You'd want to uncover what are the relevant dimensions of movies in terms of people's preferences. Maybe people care whether it has a lot of action, whether it has a lot of good special effects, whether it has a lot of romance, something like that. That would be a latent descriptor of the movie. And correspondingly, we need this for the user. We need to say to what extent does the user care about action or special effects or romance. And if these two representations are in alignment, so if the properties of the item are similar to the properties of the user, that would mean that user is likely to positively interact with that product. So to make that a bit more mathsy, you can think about that in terms of something like matrix factorization. Imagine you're given this giant matrix, most of whose entries are actually missing. It describes users against items and all of the observed ratings. What you'd like to do is uncover some low-dimensional structure in this matrix that explains the observed relationship. So you're saying we'll decompose this matrix into two low-ranked terms. one of which describes the preferences of each user, and one of which describes the properties of each item. So yeah, you should predict a high number when the preferences are similar to the properties, and a low number when the preferences are different from the properties. Yeah.
Can you elaborate more on that decomposition?
Yeah, actually, let me finish this slide, which will maybe make it clear. And then if it's not clear, then I can elaborate on it a bit more. So this is essentially the predictor of one entry in that matrix. So if you think about position u, comma I in this giant matrix, then I'm going to estimate it as follows. I'm going to say it's equal to a global offset, which you can think about as being like the average rating. There's user and item biases, which would be like, is the user generous with their rating? Does the item tend to receive high ratings? Plus this low rank term. So this is where the matrix factorization comes in. You have, say, k dimensions that describe the user and k dimensions that describe the item. And that's a matrix factorization formulation. That kind of makes sense. And yeah, these two factors here are exactly what I was showing in the previous slide at a high level, right? So they're the properties of the item and the preferences of the user, which ought to be aligned.
Do you allow the user to have multiple preferences? Like on Fridays, I like romances, but on weekdays, it's action film?
Not yet.
Okay.
That'll show up though, yeah. So later on, we'll add another comma here and we'll say u, comma I, comma t for a time point, and that can handle, I don't know, periodicity, the user getting older, or whatever. And we'll look at specific things that are relevant when you're making recommendations for fashion. Okay, so just a tiny bit more before I get into the kind of meat of visual recommendation. How do you actually estimate all of these variables? I don't want to spend this talk going on about optimization or anything, but all we do is set this up as some kind of regression problem, is what this looks like, where we're given the real observed ratings, so the training data by a bunch of users, and we'd like to estimate these model parameters, the offset, biases, and low dimensional factors, such that the ratings predicted by the model are as similar as possible to the training ratings. This is in some least squares sense. There's a slightly different version of this problem. This is so the last one is for predicting ratings. This is if we want to predict purchases. The way it's usually set up is you take two items, one that the user did purchase and one that they did not purchase, and you try to estimate the difference between these two. So you say the user should be more compatible with the thing they did purchase than the thing they did not purchase. So that's just it's a nice optimization trick that has some good properties, but that's all I'm going to say about optimization. You can do gradient descent or whatever to fit this thing. What's really important is that all we're going to do from now on is say, how can we extend this model to make it more complicated? All this model does is estimate latent interactions between preferences and properties. How can we add temporal dynamics there? How can we add visual features there? How can we add whatever else you like? All we're going to do is sort of put more complicated pieces in place of this one. Okay, so that's background. So there's two parts. First of all is to make sort of visually aware systems to recommend items to users. And second, we'll use the same framework to recommend items to items, if you like. So this is the model we have so far. It's a pretty effective model. This is the kind of model that sort of won $1 million in the Netflix prize so many years back, if you were following then. But where does it not work well? So one issue is that it's very bad for kind of obscure items or long-tail data. That's going to be specifically an issue when talking about things like clothing, where new inventory is introduced all the time. You have brand new things. This model is very bad. In particular, think about this high-dimensional item term. You can't possibly estimate the reasons somebody liked or disliked something if you've never seen anyone rate it, or if you've only seen a few people purchase it or something like that. You need to have many, many observations before you can estimate these multi-dimensional factors. So yeah, not good for new items. And third issue is that it has no notion of temporal evolution. It's just a static model. So those are the things we'll address. Another issue is that there's no interpretation of these things. You know, I talked about things like action and special effects and romance in movies or something. That's not really what this model gives you. It gives you a latent variable, which is just a vector of real numbers, and you have no idea what those dimensions mean. You can try and do some post hoc analysis maybe, but that may not be particularly satisfactory. It would be better if we could kind of bake into the model what do these dimensions actually represent. And so yeah, mostly we're going to do this on Amazon data, but think about another data set we experimented on. This is Tradesy. It's a women's clothing trading website. This is a really, really challenging setting in which to build recommender systems because the item shows up, somebody trades it, and then the item is gone forever. You sort of see one shot of each item, right? So you can't quite train this kind of model that depends on a high-dimensional latent representation of the item. If you see it only once, then it's gone forever. Okay, so those are the problems. These are the kind of things we're going to try and fix by using visual features. I mean, in essence, we're going to say, can we take this model, which has this notion of compatibility in terms of latent item properties and latent user preferences, and replace it by one where we have manifest or observed features. So can we replace it by a model that uses something like the visual descriptor of the item in question? You know, we have these very high-dimensional visual features that come from our convolutional neural network or whatever other visual features you like. Why couldn't we replace this model so that instead of using latent item properties, it'll just use observed item properties, which are available even for brand new items? Yeah. So now what we'll be learning is we're given the descriptor of the item, and for each user we're saying how much is that user attracted to each of the visual dimensions. Do they like this color? Do they dislike this shape? So on and so forth. Okay, so it's a nice idea, but it still has some problems. The main one being is that these features are incredibly high dimensional. You know, you have a 4,000 dimensional visual feature. It's still not going to be very easy to go and fit, in fact it may be even worse than it was before, to try and fit this preference vector for each user that says which of 4,000 visual dimensions are they attracted to. It's not like they've purchased 4,000 things necessarily. So this problem is going to be sort of drastically underspecified. The other problem is just that most of these visual features are probably not relevant, right? These visual features, I mean, these ones come from a model trained on ImageNet, which is this giant image data set. They're going to describe, I don't know, category, shape, color, gradients. I mean, they even have features that are discriminative, things like different dog breeds, cat breeds, who knows what. Most of these features are not going to be very relevant to our specific problem of recommending clothing or something like that. So sort of have two problems. Most of our features are probably junk, and even if they were not, we have too few observations from each user to accurately fit a model. So the way we're going to get around this is by trying to come up with some subset or combinations of these features that are actually relevant to people's opinions. So the way we would do that is take this very, very high dimensional embedding and try and project it by its linear transformation into some, by linear embedding into some low number of dimensions. So given our 4,000 dimensional image vector, we're going to learn some 4,000 by k, where k is much smaller than 4,000, of course. Maybe it's just 10 or 20, embedding. And now what we would have to do is learn for each user how much are they attracted to each of these, say, 20 embedded dimensions. And yeah, you might think, well, what is this embedding? Again, that's something we learned from the data. So we want to say, can we estimate this embedding such that it will be best at discriminating purchases versus non-purchases? So kind of intuitively, you would think each of these embedded dimensions is going to capture some notion of what you would call style, right? So maybe one style is a combination of some color and some texture together with the item being a shoe. Some other style is not related to the category, but it's related to items just being hot pink because you like to buy everything in hot pink, and things like that. So you've taken these visual dimensions that are way too high dimensional and encode all sorts of junk, and you sort of found what is the low dimensional structure here such that each of the dimensions explains the variance in people's purchases, and that's going to be something like style. Okay, so this is kind of our new model. In addition to this, we stick the old model back in. So we also have some latent item properties and some latent user preferences. The idea being visual features can't explain everything, right? If you're purchasing something like clothes on Amazon, well, obviously the visual features are a big part of your decision. I don't think you would buy clothes on Amazon if they didn't show pictures, right? So they must convey some information. But there are all sorts of other features that are not going to be revealed by the visual characteristics, right? They could be, I don't know, build quality, price, particular brands, or any other features that guide your decision but are not revealed by the visual characteristics. And what this actually means is that for brand new items, you still can't estimate these things. For a brand new item, you will estimate the prediction based only on the visual features, but as you observe more and more observations of people purchasing or not purchasing this item, you'll uncover some latent characteristics as well that might explain more information that wasn't present in the visual features. Okay, so this is kind of what the complete pipeline looks like. You have some very high dimensional image feature, you're embedding it into some low number of dimensions, adding some latent dimensions to that. That's your item descriptor. Correspondingly, you have a user descriptor, and that's how you make your prediction. Okay, so that's a reasonably effective model. I'll sort of talk about how it performs in a minute, but the last thing we want to do with it is to say, how can we add things like temporal dynamics? We're talking about things like fashion, things like clothing recommendation. Obviously, we know things like fashion change over time, so the visual characteristics people are attracted to ought to be different based on when they are evaluating the model. So how are we going to do that? Well, to put it in the most general form, we'd like to take this model that takes a user and an item and predicts compatibility between them, and replace it by a model that takes a user, an item, and a timestamp and predicts compatibility. So you can think, well, maybe any of these terms could change as a function of time. Maybe the embedding, which says what are the dimensions of style. Maybe that changes over time. Maybe, I don't know, these latent variables like which might include brand or price or something. Maybe particular brands come and go over time. Or maybe these user terms. Maybe, I don't know, as a user gets older, they go from being an undergrad to a PhD student. They tend to buy different types of clothes. I'm not sure. So any of these different terms could have some kind of temporal evolution. And I'll just talk about a few ways we can bake that into the model. So this will get a bit mathsy, but I'll just talk about the high-level ideas. So the first one we might like to do is say, how can we make this embedding temporally evolving? So what does the embedding say? It kind of says, what are the low-dimensional notions of visual style that we'd like to capture? Those can obviously change over time, and those can be captured by having an evolving embedding. So in the simplest case, just think time could be the year or the month or whatever granularity you can afford, and you fit a different embedding for then each month.
Do you have to pick up front how many dimensions the embedding is? So you say 20?
Yeah. So you've got to pick that up front. I mean, in practice, following machine learning protocol, you do that by cross-validation or something like that. So you try it for 5, 10, 20, 50, and see at what point does it stop helping. Really just, in this data set especially, not many dimensions are affordable. So you don't have very many observations per user, so you can't necessarily uncover extremely fine-grained notions of style. And there's another issue, which is just that the data sets and the models are extremely big. So there's a question of how many dimensions can you actually afford to train the thing on. Obviously this is a 4,000 by, say, 20 embedding. So that's 4,000 by 20 parameters. You now have it evolving over time. So maybe you have 50 of these things. So it's 4,000 by 20 by 50. You can see how it blows up, especially when we add the temporal dimension into it. All this is some funky optimization trick, so that instead of fitting a different embedding every single month, you fit you fit a global embedding, which is kind of like the static notions of style, and we say that changes mostly in it's mostly the weighting of each of those dimensions that change, plus some very small offset. Really what we're saying here, to be mathematical about it, is we're saying that the evolution breaks down into a low rank plus a sparse component. It's just kind of a standard idea from optimization to avoid overfitting when you just have some blowout of parameters. Okay, so that's our first idea of temporal evolution. We have the global embedding of the different dimensions of style changing over time. The next thing we can do is say, well, maybe a user's preference towards each of these dimensions changes over time. So even if the dimensions of style will be static, you're still going to change. Maybe you like hot pink when you're young, but as you get older, or you like gothic colors when you're young, but as you get older, that becomes uncool. So for you personally, as a function of time, your preference towards each of these dimensions changes. So we just fit this with a two-dimensional parametric function. This is an idea we stole from someone's KDD paper. This is just a function that says, okay, your preferences can go up, or they can go down over time, or they can have kind of different elbow shapes. So that's all this complicated function with a sign and a power is doing. It's allowing you to fit these different types of curves that say, essentially, does a user's preference go up or down as time goes on with respect to each of these dimensions? And sort of how steeply does it do that? Right, and the third thing is, this is kind of a weird one, is that this is not really a visual temporal dynamic, but you can just say, well, over time, different categories might become more or less popular. So you might think, I don't know, what's a very obvious case? Winter coats become popular each winter, and then they lose popularity. Or maybe 20 years ago, Amazon didn't sell socks, and then 10 years ago, they started selling socks, and suddenly socks become very popular. This is kind of more of a moral lesson. It's like you really want to include these very boring features in the model that explain a lot of variance in the predictions so that the visual features don't have to account for them, right? You can think, well, yeah, my visual features can estimate whether something is a sock or not, so they can already explain the fact that socks are becoming more popular, but socks being sold on Amazon is not fashion, right? It's a kind of a boring property of Amazon itself. And if you're trying to make these models interpretable, in other words, you're trying to understand what are the dimensions of fashion, you sort of want to explain away all of the boring, high variance properties that are just due to the weird idiosyncrasies of the data set as much as possible, so that all that's left over is fashion. So you don't actually need to do this, but if you don't do it, you'll get sort of very meaningless, boring visual dimensions. Okay, so that's kind of, I'm just giving you a flavor of this thing. Of course, the model is some giant Frankenstein construction that considers all kinds of different visual and temporal effects. I think I got most of them though. You sort of have this, you have the, we have the temporally evolving terms, which includes the embeddings. We have the non-visual latent terms, and we have the evolving user terms as well. And they all go together. Does the thing actually work well? I mean, sure it does. This is a giant table with way too much stuff in it, but there's a few sort of relevant things here. So what are the values actually being predicted? This is for, say, women's clothing on Amazon. This is just some baseline. Going back to our optimization problem before, this is the fraction of times we can correctly predict, given a purchased versus a non-purchased item, that the purchased one would be the one with higher preference. So 70% of the time we correctly identify out of two items which one the user purchased. So various different baselines here. The first one is one that has no visual features, no temporal evolution. Then we sort of add in the visual features. Then we add in different pieces of temporal evolution gradually until we kind of get the final model. And yeah, you get a reasonably substantial, by some definition, improvement over the non-visual model. Where you get the largest improvement, of course, is in what we call cold start items. In this case, this is items that had, I think, fewer than 5 purchases. So not surprisingly, these sort of traditional models based on matrix factorization can't really do anything, because you can't uncover the multidimensional reasons people liked or disliked something, but you can do much better if you use visual features. You can do, you know, almost as well as you could do for well-established items. And of course, yeah, you can also make these these nice visualizations, which are kind of what gets these papers accepted, I think. So this is taking our sort of medium dimensionality embedding of style dimensions and then embedding it down even further into just 2 dimensions so that you can draw it on a slide, and visualizing a few locations to say, okay, these are different notions of style that have been discovered by the model. So I'm not sure how much relevant information you can extract from this picture, or if you can actually tell me, what is the name for this style? No idea. Yeah, me neither. But it does capture sort of semantically reasonable notions that say, all right, high-heeled shoes are kind of they may be closer to sort of flat business shoes than they are to sneakers or something like that. So what this model is trying to do is project items to be nearby if users who like one item would be likely to also purchase the other. Yeah. So you would think maybe there are some other more complex notions in here, like, yes, okay, well, of course shoes go near sneakers, but sneakers should also go somewhat near, I don't know that it's visualized anywhere here, but sneakers should be somewhat near to running shorts or something like that, right? Those items are not visually particularly similar, but they're similar in terms of how people purchase them because they're both used for running. And yeah, also with this kind of model, you can get these nice notions of what was fashionable when. I mean, this data set goes back to sort of 2005 when Amazon started selling clothing, and you can kind of see this is an example of just one fashion that gradually became fashionable over time and then lost fashionability towards 2014, which is why maybe none of you can name that fashion style for me. Okay, so that's kind of user to item recommendation. Unless there are any pressing questions about that, go for
I have
it.
a question. You mentioned that we are making recommendations for individual customers. Do we know, or do we have any more information about the customers themselves so that we can have a representative of customers with different purchase histories together? Or?
I mean, I don't know anything about the customers because I don't work for Amazon, I guess. They might have additional information about the customers that should be useful. The only thing we can learn about the customers is what we can glean from their purchase history. So what do their past interactions tell us about them? And that ought to be reasonably effective, at least for customers who are not brand new to the system. And this model is going to give us a notion of which customers are similar to other customers, because we're learning this low-dimensional representation of a customer. So we can say 2 people are similar to each other if they have similar embeddings, in which case they're likely to purchase similar things. Yeah?
You motivated the cold start problem with the items.
Mm-hmm.
You may not have many items, or items might come and go, new fashions come in. What about the cold start problem for the user?
Yeah.
You have very little data about what they've liked or what they've looked at.
Yeah.
How do you...
Here with this model, we can't do much for the cold start user problem. But in general, if you wanted to solve the cold start user problem, you'd have to say, well, what do I know about the user when they are new? Or what questions could I ask the user when they are new? For instance, maybe you know their social network. Even if they're a new user to Amazon, maybe they log in via their Facebook. So you can say, well, they're probably similar to their friends. Or maybe you have some features that describe their demographics. So you know their age and their gender and where they live. And that would tell you something about what they're likely to purchase as well. Something fairly superficial perhaps, but it'll give you a little bit of information. Or you could say, when a new user arrives, just get them to rank 5 products for you. And that would be sort of a good model initially. But yeah, in this case, if a user is new, we really don't have any information about them. We can just recommend them the most popular items or something like that. Okay. Yeah, one more?
Going back to the previous slide, it seems to me that a lot of photos, they have the same style, same color, same angle, and so is that like a necessary requirement for your formula to work, is that the user knows what style they should be utilizing while taking the photo?
I mean, there's sort of, I think, 2 points there. One is in terms of the images looking the same. That's more of a characteristic of the data set, I think. It's just, this is how product images happen to look on Amazon. In terms of items, like nearby items having the same style, well, that's kind of what you would want the model to uncover, right? You would want this to be, rather than being a random projection of items, you would want this to be items that belong to the same style being near each other. That's what sort of makes the model effective.
But let's say like a seller has like a background in the picture, and then maybe he took the issue and like force or something.
Sure.
Maybe categorize that to the same.
Yeah, so we're kind of hostage here to the quality of the data that we train on. So Amazon data is nice in this sense because it's very, very clean and the images all look the same. If we got an image that looked drastically different from everything we trained on, the model would not work well. But if you did have the kind of variance you're talking about when you trained the model, it would cause no problems because you'd learn to ignore the background and focus on the object in the middle of the image. Yeah, it's just that, we don't have that at training time. We've used this on other data sets, like Tradesy and even some website for art recommendation, where the images are not quite as clean on Amazon. But yeah, as long as you have that at training, it should be fine. Yeah?
So when one customer make a purchase, how do you know if it's because of the visualization or because of the item description? And another thing is, I believe the matrix to reduce the rank of the visualization to a little bit lower dimension is globally the same. It's a function of the time, and the gamma function of each is varied by users, right?
Yeah.
Estimated by previous statistical data using interpolation. Is that how the gamma function is estimated?
Yeah. So it's all estimated using. You're trying to set the parameters such that the model assigns high scores to things that were purchased and low scores to things that were not purchased.
Yeah, then the problem comes, how do you distinguish between, like, whether if the customer makes the purchase, how do you know if it's due to the visualization?
Yeah, so that's something we're going to have to uncover by observing the item multiple times. Like we have these two terms here, one of which describes the visual characteristics, one of which describes all of the non-visual characteristics. So only once you've observed the item multiple times will you be able to fit these two parameters. If it's primarily purchased because of its visual characteristics, this term should be very small. If it's primarily purchased because of its non-visual characteristics, this term should be very large.
Oh.
The non-visual term should dominate the visual term. Make sense?
Yeah.
Okay, so let's just adapt this problem a little bit so that we can talk about item-to-item recommendation rather than item-to-user recommendation. So it's going to be a very, very similar prediction task to what we had before, but rather than being given a user U and an item I, we're going to be given two items, X and Y, and we'd like to predict whether they're related. So we'd like to do something like come up with a distance function between two items such that nearby items are likely to be related. And what does related mean? It's going to mean something like co-purchased or co-viewed. So these are two notions of items being related. This is data we got again from Amazon. So you have some item, and you have all of these observed relationships this is based on clicks essentially. People who viewed X also viewed Y, and this is based on co-purchases, so people who bought X also bought Y. So can we uncover those kinds of relationships automatically? And why are those useful for recommendation? Well, the first of these, this idea that they were clicked together, might be a hint up to some noise that those two items would be substitutable for each other. But if they were bought together, it might be some hint that they're complementary items. So they would actually go together to form an outfit. So this first notion of two things being clicked together, that's a notion that probably corresponds to something like sort of raw visual similarity. But this idea of two items being brought together, it's somehow semantically more complicated, right? You don't want to wear like lounge suits where your shirts look exactly the same as your pants. You want to come up with something where, you have this notion of complementarity. They should be similar in some dimensions, different in others. Yeah.
Is this kind of tied to the interface, how it presents each item? I mean, do we have the knowledge about whether the user actually typed in for a specific item, or does it just did she or he click on the next item that Amazon just presented?
No, so we don't know if these data we collected are based on they clicked on it because they found it organically versus they clicked on it whether it was the result of the interface. So there could be a feedback loop or some issue like that in the data set. And again, we're kind of hostage to the quality of the data. We're learning, you can argue whether we're learning something that's specific to Amazon or whether we're learning some globally true notion of the zeitgeist of style or something like that. Later on, we'll try and make arguments that what we can learn from Amazon is somehow consistent with what humans would consider to be style, rather than just, some weird idiosyncrasy about the Amazon interface. We'll get to that. Okay, so again, we're using this Amazon data, but now instead of having things like purchases, we have now co-purchases or co-clicks, some of which correspond to the notion of substitutability and some of which correspond to complementarity. So we're going to fit this in exactly the same way, so I won't say much more about optimization. We're just going to try and estimate some distance function such that things that are related, according to our training data, are given a very high probability, and things that are not related are given a very low probability. So it's still this sort of maximum likelihood type of training. So like before, we're doing prediction based on the object's visual features. What's different from before, of course, is that we now have two objects rather than just one object. So we're looking at the relationship between two sets of high-dimensional visual features. So again, what's the simplest thing we could do? We could take our 4,000 dimensional features and say our distance function looks like this. Just go through all of the 4,000 dimensions and say, are the two objects similar or not in each of those visual dimensions? And maybe we could learn some weighting function that says, okay, which dimensions of similarity are relevant, which dimensions of similarity are not relevant. Okay? And again, it's going to have some, maybe more of the same limitations that we had before. We have this very, very high dimensional feature vector. Most of those dimensions are not relevant to visual style. And finally, it captures sort of too rigid a notion of similarity, especially for things like co-purchases or for constructing outfits. You don't want your pants and your shirt to look maximally similar, at least not in the sort of crudest way. So we'll try and do the same trick where we'll try and learn embeddings that correspond to the notion of visual style. So instead of those embeddings trying to predict purchase behavior, we're now saying, can we learn this embedding? Can we find the dimensions of style such that items that are co-clicked or items that are co-purchased will be embedded to nearby positions? And then we fit it in exactly the same way. Just quickly some results, which I don't think the numerical values of the results are too exciting, but we can kind of vary the number of dimensions we have in the model, and we can try and see how well, again, the model distinguishes a pair of items that were co-purchased versus a pair of items that were not co-purchased. And for some shoes, there turn out to be extremely discriminative visual features that can say that things are co-purchased. You can find people who purchase running shoes are much more likely to purchase other running shoes than they are to purchase high heels or something like that. So there are some simple visual features that turn out to be incredibly discriminative for this task. And that's explaining actually sort of things that were co-clicked. It's also very good for explaining things that were co-bought, like outfits. That could be shoes that go with pants or shoes that go with shirts. There are also apparently visual features that are very discriminative at that task.
Julian, you have the text of the stuff also.
Yes.
So in the running shoe case, you wouldn't even need to look at the picture to know they were both running shoes.
Yeah, certainly. For the sake of evaluating this thing, a very simple baseline that we also, you don't have results in the slides, but a very simple baseline is to say, let's use that explicit information like the object category and say, how well does just using the category, which is quite fine-grained, it tells you whether it's a squash shoe or a tennis shoe and things like that. So just using that category information alone, how well does that predict whether things would be co-purchased or not co-purchased? And it works pretty well, actually. But yeah, there's certainly substantially more information in the visual features than what is present in the category information alone. Okay, so yeah. Finally, we can actually use these types of models to generate recommendations. So given some item, we can generate a set of recommendations that belong to different categories but are in the same visual style. So, you know, this shoe goes with this shirt, this pair of pants, this accessory, something like that. So, you know, if you purchase a flannel shirt, maybe that goes with jack boots, a balaclava, and track pants. You know, this is a genuine recommendation made by the system. It's not necessarily a notion of what's fashionable, but it's at least a notion of what real Amazon users are actually doing. And yeah, all kinds of other notions of fashion. Again, you know, you have, if you're buying a camo Chevrolet shirt, you probably want a leather vest as well, yeah? And again, I'm not saying, the point is to understand that it's not fashion in the sort of high fashion sense. It's fashion in the sense of what kind of things would Amazon users, or I don't know, a representative sample of the population think would go together. And, you know, people who buy their clothes on Amazon, I count myself among them, maybe are not the highest fashion individuals. So yeah, back to this question before of whether we can kind of externally validate this and say, well, have we uncovered a notion of fashion, or have we just uncovered something specific about Amazon? We wanted to ask, well, can we take some external labels of what is fashionable or what is non-fashionable and see whether this model can estimate whether sort of outfits in the wild are fashionable or not. So this is from a TV show, Top Gear. Who watches Top Gear? One person, two, three, four. Okay, not very many. So I don't know, there's some pretty reliable ground truth about which of the Top Gear presenters are fashionable. This one is kind of a foppish English gentleman, and this is more of a English lad. And yeah, the model kind of successfully identifies that the gentleman is much more fashionable. I think that example doesn't, I thought this would make things clearer to people, but it turns out nobody ever watches this show. A show that all of you have surely watched is one called What Not to Wear. Yeah? Not so much. Well, no one's going to admit to it anyway. So this is a show where these women are volunteered by people who are ostensibly their friends for an outfit makeover, right? So they come in with this putatively unfashionable outfit, and then a fashion expert designs a new personalized outfit for them. Yeah? Makes sense? Good premise for a reality show. And what we can then measure is the change in log likelihood of their old outfits compared to the new ones. And yeah, the model, you know, the take home from these results is the model statistically significantly realizes that the new outfits are more fashionable than the old ones. Okay, so it's kind of uncovering a notion of fashion that's at least consistent with this television show, if not the population at large. Okay, so I think that's about it from me, so I can finish on time and have plenty of time for more questions. Of course, this is mostly the work of my wonderful graduate students. This is a couple of papers of Ruining Hees, he published in AAAI. This is sort of the non-temporal version plus the temporal version, and this is one with the item-to-item recommendation we did with a bunch of Australians and all kinds of other folks. So thanks.